Hello everyone, I welcome you to the class of Unmanned Air Vehicle Design on today's topic tail design. Functions of the tail. In a conventional aircraft, the tail typically comprises horizontal tail and vertical tail. If we take the aircraft structure, the empennage part, this part is vertical tail, and if we look from the front view, this is horizontal tail. These components perform the following primary functions. First one, to bring back the aircraft into equilibrium position, we trim the angle of attack which has been increased due to gust loads. If this is an aircraft, right, and if it experiences any gust load during the cruise, it will tend to move the position of the nose of the aircraft upwards. So suppose this is the equilibrium position and here there is a slight change in the angle of attack. So it is 1 degree change. Assumption is 1 degree change here. So to regain this change of 1 degree, we use elevator which is on the horizontal tail, at the trailing part of the horizontal tail, to bring back this to equilibrium position. That is, if the aircraft is like this, it has changed its position like this. Now I want to get it back to the level flight, equilibrium position. Again, in this way, I will be trimming it using an elevator, such that the lift is increased here, the nose comes down. Same thing is with rudder, which is for trimming in the directional side. If any gust loads are acting from this direction, this will tend to move aircraft from its flight axis. It will push it in this direction. This is the change in flight angle, right? So to bring it back to the equilibrium position, we'll trim it using the rudder which is on the vertical tail. This is the rudder which changes the direction. But once we attain this stability, we call it as longitudinal stability and directional stability. The stability which is due to elevator is called longitudinal stability, and the stability which is obtained via rudder, we call it as directional stability. These stabilities are achieved through control surfaces: elevator, longitudinal control, rudder, directional control. The tail design process. Aircraft design is an iterative process, and tail design is repeated until optimal configuration is achieved. We will test with n number of designs to ensure the requirements are satisfied. Most parameters are finalized via technical calculations, and few parameters require engineering judgment or selection. These are existing data or historical trends which are available. Based upon these historical trends, we select the best tail for our requirements. Based upon the requirements and the historical trends which are available, based on these two, we'll use it. The design approach. Horizontal and vertical tail designs can proceed almost in parallel. Vertical tail design includes a special step, that is spin recovery, which considers the effect of the horizontal tail or vertical tail performance. This is the tail design flowchart for vertical tail and horizontal tail. There are two ways. First one is to identify and prioritize the tail design requirements, and then we'll go with the tail configuration. Once tail configuration is being selected, then we'll go with vertical tail and horizontal tail parallelly. We'll select vertical tail volume coefficient, and we'll select horizontal tail location. Horizontal tail location, after choosing that, we'll go with select horizontal tail volume coefficient, that is VH, and for this it is VV and this is VH. And in vertical tail, after selecting the volume coefficient, we'll determine the tail arm, that is the length of the tail, and then determine its planform area. Then we'll determine the airfoil selection, the airfoil which is been chosen based upon its specifications. And once the airfoil selection is done, we'll find the aspect ratio and taper ratios along with the sweep angle. Then we'll determine the setting angle. Then we'll calculate span, mean aerodynamic chord, root chord, tip chord. After that, we'll check for spin recovery. If spin recovery is possible, we'll analyze it for longitudinal stability optimization. If not, then we'll come back to the selection of vertical tail volume coefficient again. Same thing with the horizontal tail. After the selection of horizontal tail location, we'll select the horizontal tail volume coefficient. Then we'll go with determining the optimum tail arm length. Then we'll determine the planform area. Then airfoil section. Then we'll determine sweep and dihedral angles. Then we'll determine the aspect and taper ratios. We'll calculate the setting angle. We'll calculate span, mean aerodynamic center, root chord, tip chord, and we'll check for tail stall. If it is stalling is fine, then we'll come back to this directional stability and optimization. If it is no, we'll come back to this select horizontal tail location. The term tail refers to the combination of horizontal and vertical tails. Initial step in tail design. Tail configuration selection is not a result of calculations but a decision based on evaluation and design requirements. It involves reasoning, logic, and comparison of various options. Tail design requirements must satisfy longitudinal, directional, and lateral trims, longitudinal, directional, and lateral stability. It should also satisfy controllability and manufacturability, handling qualities, stealth if it is a military based unmanned air vehicles, operational and airworthiness requirements, cost competitiveness, and size constraints. Tail configuration options which are available, they include aft tail and single vertical tail. Aft tail here is this one, the conventional tail, which will be on the empennage part. Then we have aft tail with twin vertical tail. In some aircrafts, in some configurations, we have a tail before the wing. In some aircrafts, like Su-35 and Rafale, we have canard options, this is canard, which is ahead of the wing. Behind the wing, we call it as aft tail, and this we call it as, in front of the wing, we call it as canard. So we'll have canard plus aft vertical tail, canard plus wingtip vertical tails. Triplane configuration. Then we have tailless, which is delta wing with single vertical tail, and then we have flying wing where there is no formal tail. There are many sub configurations for aft tail configuration. For example, conventional, T-tail, cruciform, H-tail, triple tail, V-tail, inverted V-tail, improved V. Then we have Y-tail, twin vertical tail, boom mounted vertical tail, inverted boom mounted tails, twin tail, and U-tail. Examples for unmanned air vehicles, we have Global Hawk for V-tail. MQ-9 Reaper unmanned air vehicle is having Y-tail configuration. Scan Eagle is having wingtip vertical tails, and Arcturns is having T-tail. Special UAV tail designs, vertical tail, which is underneath the fuselage. For example, in Predator MQ9 unmanned air vehicle, the purpose is to enable unobstructed satellite communication, and it affects no rotation during takeoff, and it's lift off at cruising angle of attack when lift is greater than the weight. Horizontal tail location options, we have aft tail and canard. Canard will be the foreplane, tail first, then wing, and then after aft wing tail we have, and then we have a conventional tail which is aft tail here. Comparisons, tail configuration, stall behavior. For canard, it avoids deep stall, and for conventional tail, it may enter deep stall. For efficiency, canard is having higher and conventional tail will be having lower. Static margin, canard will have smaller, conventional tail will have higher. Lift contribution, canard will have positive lift contribution and conventional tail will have often negative contribution. Trim, during canard it is more efficient and conventional tail it is less efficient. For control, canard is less efficient and conventional tail is more efficient. Analysis complexity, canard is having higher, conventional tail is having lower. Example, Global Hawk, it uses V-tail to mount engine above the fuselage. It shields exhaust from infrared sensors. It minimizes aerodynamic penalty and it lowers maneuverability, is acceptable for reconnaissance load. Right. It has very low maneuverability as it will be having the role of reconnaissance. So, when an aircraft is opted for this reconnaissance role, it will be having high aspect ratios, and when an unmanned air vehicle is having a high aspect ratio, it has to compromise with the maneuverability. It will be having very low maneuverability. So, when we are going with this kind of aircraft, we have to compromise with maneuverability. Tail is initially designed for longitudinal trim, especially for cruise flight. Later refined for stability and control. Elevator effects are ignored in the early design phase, and majority of flight time is in cruise, making it the crucial condition for the design. As a designer, you will be only focused on cruise because this is the 90% of the aircraft range. So, you will be focusing only for the cruise. Tail design process is broadly similar for manned and unmanned aircraft. Tail parameters to be determined. First one is tail location, whether it is aft tail or it is a canard. Then planform area, tail arm, airfoil section, aspect ratio of the horizontal tail, taper ratio of the horizontal tail, tip chord of the horizontal tail, root chord of the horizontal tail, mean aerodynamic chord of the horizontal tail, span of the horizontal tail, sweep angle of the horizontal tail, dihedral angle of the horizontal tail, tail installation method, tail incidence angle. These are the few parameters which are to be determined when we are working with the horizontal tail design. Tail area and tail arm are interrelated parameters in tail design. Both are determined simultaneously to satisfy longitudinal trim and stability. Trim condition for non-dimensional trim equation is Cm naught plus Cl h naught minus h minus Vh CLH equals to 0. This equation ensures aircraft trim in cruise and critical for horizontal tail design. This is CL of horizontal tail. This is tail volume coefficient. Okay. This is the CL with distance with respect to the distance, and this is moment with respect to wing and fuselage interaction. Tail area and tail arm length are interrelated parameters in tail design. Both are determined simultaneously, which ensures aircraft trim in cruise and critical for horizontal tail sizing. Cm0WF is wing fuselage pitching moment coefficient, which is approximately 0.06, negative 0.06. CL is aircraft cruise lift coefficient, which is from the lift equation. H0 is non-dimensional location of wing fuselage aerodynamic center, which is typically 0.25. H is non-dimensional CG, which varies between 0.1 to 0.3. VH is horizontal tail volume coefficient. CLH is tail lift coefficient at cruise. Horizontal tail volume coefficient VH equals to L into SH by CS, which combines tail arm and tail area, and this typical range is between 0.4 to 1.2. It is used for preliminary sizing of horizontal tail, and static longitudinal equation is Cm alpha equals to CL alpha W H minus H0 minus CL alpha H neta H into SH by S, which is L by C minus H into 1 minus d epsilon by d alpha. The UAV static longitudinal stability is examined through the sign of the longitudinal stability derivative Cm alpha or the location of the aircraft neutral point. If Cm alpha is less than 0, it implies neutral point is aft of CG, and if it is unstable, redesign the tail parameters. If this condition is not satisfied, in case it is not satisfied, we have to redesign the tail design parameters. The influence of tail arm: longer tail arm will have smaller tail area, shorter tail arm will have larger tail area. Both configurations can meet trim requirements, but for tail arm which is longer, tail area is smaller, it will have lower SH, lighter tail, and disadvantages: structural weight may increase due to the boom. Shorter tail arm length will have larger tail area, which will have a compact design, and it may increase drag and tail weight. Optimizing tail arm: optimum length is a trade-off between tail weight, aircraft drag, trim and stability requirements, and it should be determined by iterative analysis, balancing all design goals. The tail plane must generate both positive lift and negative lift to trim the aircraft under various CG conditions. Therefore, the airfoils must exhibit symmetric performance over a wide range of angle of attack, and the key criteria for tail airfoil section is high lift curve slope, which enhances tail authority and trim control. It is important for ensuring sufficient lift capability in a compact tail. Symmetric performance about zero angle of attack. Tail may need to produce lift in both directions, which is best achieved using a symmetric airfoil, that is NACA 0009 or NACA 0012 or NACA 0024. In NACA 5-digit and 6-digit airfoils, a 0 third digit signifies symmetry. Example of a tail airfoil: NACA 0009, which is symmetric airfoil, which has a thin profile. It has good linear lift characteristics over wide range of angle of attack. It is suitable for subsonic and light unmanned air vehicles. Airfoil selection guidelines for horizontal tail. The first parameter is lift curve slope. Desired feature is high. The reason behind is for better control effectiveness. The second parameter is symmetry. Desired feature is yes, to produce positive and negative lift. Compressibility is delayed, ensuring thin section and lower Mach number. Thickness, thin is approximately 2% of mean aerodynamic chord, which reduces drag, avoids shocks. Angle of attack range is wide usable, which trim across CG variations. Conclusion of this lecture: the tail assembly in a conventional aircraft consisting of the horizontal and vertical tail is essential for achieving trim in both longitudinal and directional axis, providing stability in flight dynamics. Proper airfoil selection, particularly for the horizontal tail, ensures capability to generate positive and negative lift as when required, adequate performance over a wide range of angles of attack, operation free from compressibility effects at cruising speeds. Overall tail design directly impacts the controllability, stability and safety of the aircraft during all phases of flight. The references used for this lecture are Design of Unmanned Air Vehicle Systems by Sadare Mohammed, Aircraft Design, a Conceptual Approach by AIAA, author is Daniel P. Raymer, and Introduction to Flight, McGraw-Hill publication, author Anderson J.D. Thank you.